So what I'm doing today is I'm going over the butane lab, and this lab, what we had is we had a canister of butane, and that canister of butane was basically a refillable canister. And in this canister of butane, it said it was quadruple refined, okay, which means that this container had butane gas of very high percentage. Now, when they talk about refined or talk about quadruple refined, basically what they're saying is that this butane should be at a high concentration. It's very hard to separate butane from its other hydrocarbons associated with. We get butane like we do most hydrocarbons from fossil fuels or crude oil. So when we get a crude oil, let's say barrel that we get mostly domestically now, and we get this crude oil, which is a mixture of compounds, what we do is we distill it. Use a fractional distillation. Very simply, we take the entire container, all of the different compounds, and then we heat it. Okay, so applying some heat, these things evaporate. Okay, a lot of it evaporates, but we have this column, and as the gases, the evaporated compounds go up a column, the temperatures drop. And at certain temperatures, okay, what was once a gas now starts to condense into a liquid, and we collect that liquid, and it's called fractional distillation. So butane, okay, is a very small hydrocarbon. It's one that has the 4 carbons. That's what the but means. The ane means it is an alkane. So we say C4H10. That's the alkane formula. You could certainly write it this way. 4 carbons have a single bond, and then we fill the rest, making sure carbon has the 4 bonds because of its 4 valence electrons. And every one of these is an H, and we go around and round we go. So that is how we could figure out that that is butane. No big deal. So the question is, in this lab, is if it's quadruple refined, which may mean that it's been distilled this way 4 times over, because you may say, well, why would it be collecting at a certain temperature? Well, certainly butane holds its own intensive physical properties of a boiling point or condensation point. However, there's probably going to be other compounds with similar boiling points that would come with it possibly. It won't be 100% pure. So by doing it 4 times, we're supposed to have a very pure butane sample. So we're going to test the validity or how pure the sample is. If it was pure butane, okay, we would get a molecular mass that would approximate what the theoretical value is. Now, of course, a molecular mass, in this case, we have this molecule, and if we had a mole of this molecule, we'd have 4 moles of carbon. And each carbon has a mass of 12 grams per mole. So what we got here is 48, and then we have 10 hydrogens. So in 1 mole of this compound, we have 10 moles of hydrogens. I said hydrogen, but carbon came out. All right, and of course, so we have 10 of these, and a mass of 1 mole of hydrogen atoms is 1 gram, so we get 10. So what do we have here is we have a molecular mass to be 58 grams per mole. So although we, in this lab, will not be able to directly measure how pure it is, we're going to figure out molecular mass, okay? So if in fact this is pure butane, and of course we have low amount of experimental errors, we should get a molecular mass very close to 58 grams per mole. We won't be able to figure out in this lab what compounds were with it, but essentially this is a lab of getting molecular mass. So let's take some of this stuff away and talk about how we're going to do this. So in this lab, we're determining the molecular mass of butane. Now, how are we going to do this? Well, let's look at the formula. Okay, so very famous formula. Molecular mass is equal to the density, universal gas constant, temperature in Kelvin over the pressure. And if certain the universal gas constant the universal gas constant you use will drive the other units. Dirt over P is my famous way to remember this. And we, of course, have derived this from the ideal gas law formula. So if we get rid of the density and think about what that really means, it means we have grams over the volume. Okay, so this is what we need. So how are we going to do this? Well, we're going to take and we're going to, I should say, we're going to collect butane by water displacement. So we're going to take a water trough, fill it with some water. We're going to take a container. In this case, the container I'm going to use is a graduated cylinder. I don't know why it looks like a bird with a beak, but hey, that's what I'm going to use, a graduated cylinder. And we're going to fill that with water, fill that all the way to the top. We're going to put our hand over it, our red hand with a big thumb, and we're going to cover that, okay? And we're going to essentially invert it and place it into the water trough. And of course, what you're going to have is the water will still be suspended as long as it's submerged in the water bath. And the reasoning, of course, we've been through this, is that atmospheric pressure can definitely support that column of liquid. In fact, it can support up to about 32 feet of water in a column. And that's where the first unit of pressure came from. Okay, so big deal. So we've got this scenario going. So now let's get rid of my beautiful drawing there. So let's take our can. We'll take our can. It's got a little valve. Okay, and our butane can, what we're going to do is we're going to mass it out and know its initial mass. So we'll have the mass of the can, whatever that value is. And then essentially we're going to put the can under the water, press down, and let the bubbles of butane collect. And what's going to happen is the bubbles of butane is going to push the gas, is going to push the gas downward. So as the bubbles come to the surface, okay, the bubbles come up, it's going to push the liquid out. So we're going to displace it. In fact, what you're doing is you're adding gas molecules up here, and these gas molecules are pushing in all directions, including it's pressing downward. And that downward pressure, okay, is opposing the atmospheric pressure. Okay, now, of course, if the pressure in the flask here was equal to the atmospheric pressure, it would push down until they're equal. And that's where we're talking about manometers. But, so in any case, what we're going to do is we're going to press down on the can, we're going to collect the bubbles, and we're going to stop somewhere in the middle. And what we're going to do is this. We're going to gather some data. Remember our formula. Okay, the first thing that we're going to do is we're going to measure the volume of that. Now, because the graduated cylinder is upside down, the zero mark is here, but you can actually measure the volume of the gas. So we're going to have the volume. Okay, the temperature of the system. If you're using room temperature water, as we did, the temperature of the system in Kelvin is converted to Kelvin. So the temperature of the water will have a thermometer here, and we'll measure, okay, the temperature of the room, or the water, which will be the room. Okay, now after we put the can in the water to get the bubbles out, the refillable can, what we're going to do is we're going to mass the can again. And before we do that, we're going to dry the can. We're going to put a blow dryer on it. Okay, we're going to make sure all the water that, as it got wet under the water, it gets dried off. And then after we do that, we mass it again. And of course, the difference of the initial and final, okay, is going to be the mass of the butane that is in the top part of the cylinder. And that's going to be in grams. Okay, so we know the universal gas constant, so I'm almost home, okay, to get the molecular mass. Now, the pressure of the butane takes a little bit of work. And let me just clean this up here as we go forward. In order to find the molecular mass of the butane, we're going to need the pressure exerted only by the butane in here. You may say, well, of course it's butane. We added bubbles here. Well, there's a problem with collecting a gas by water displacement. One of the issues is possibly the gas could either dissolve in the water or react with the water Either way, you're not going to get the bubbles that you'd expect if it didn't do those things. Now, butane, as we can see, is the butane that we're using, of course, all butane, because it's a hydrocarbon that I just drew, is a nonpolar molecule. Okay, it has an equal distribution of electrons because the carbon bond has the same electronegativity, and the carbon to H bond is very similar. We can almost consider that to be a nonpolar bond. So the butane doesn't dissolve, it doesn't react in water, so it's a good pick or good fit to use for water displacement. But the one limitation we have, and every limitation we have with water displacement, is that water likes to evaporate. So not only am I catching in here butane, I've got butane and I have water vapor. Water's evaporating. You can't help it. So one of the limitations always with this type of system of water displacement is you're going to have the water, okay, evaporating and contributing to that pressure. So if I was to build up that flask, okay, and this would be the water coming down, we would have our butane gas, just write it as butane, all right? But then we're also going to have some water molecules in here. Now, I'm showing as a 1-to-1 ratio, but there's going to be a heck of a lot more butane, okay? So there's going to be a lot more butane, but there's going to be some molecules of water. Now, what do we care? Well, guess what? If I have some water molecules, they're going to contribute to the pressure. But again, to solve for the molecular mass of just butane, I just want the pressure just by the butane molecules. So what do we know? Well, we know something very special. When we have gases under the same conditions of temperature and pressure, then the ratio of how many particles is their ratio of their pressure, right? These gases are pretty much under the same temperature and pressure. They're in the same space. So we learned by Avogadro's hypothesis that volume and number of particles, okay, are proportionate. But if you think with that even further, if there are more butane molecules, then there is more collisions due to the butane molecules, which that means is if we know the total pressure, okay, in this top part, we have to consider that part of that pressure is due to the water, okay? And in fact, the total pressure in here should be what? The addition of both gases, and that's what Dalton's law of partial pressure. So the pressure total is equal to the partial pressure, the individual pressure, which means due to all the collisions due to the butane, plus the partial pressure of all the individual collisions of the water. And that's pretty intuitive, and we will derive that later. So it's pretty straightforward to understand. So our total pressure has two different gases. We're after just the pressure of the butane. So how do we get that? Well, we're going to have to first understand that the pressure, to even get the butane, we need the what? We need the total pressure in the container first. So the first step is to get the total pressure. Once we do that, there's a way to figure out the water, a very simple way from a table to get that. But we need pressure total first. So let's clean up some areas and let's figure out what this pressure should be. All right, so to figure out what the pressure is here, understand what you're looking at is really a manometer, okay? You have a tube with water being suspended, and you've got atmospheric pressure pushing down. So what you really have is you've got the force over the area of the atmospheric pressure kind of pushing and keeping up the water. So the atmospheric pressure is not only pushing back on this gas, it's pushing up the water. So we can think as the atmospheric pressure should be what? Higher than the pressure in here. Now, if you don't see that, okay, let's make a manometer. Let's make one of those diagrams maybe you've seen before. So I'm going to put the gas in a container, and we'll go down, and this always reminds me of like a nephron in a kidney, but hey, here we go. That was the ugliest manometer I've ever drawn. Okay, so let me try that one more time. So here we go, down and up. Okay, that'll be an open tube. All right, and I'm trying my best here. All right, it's better. Okay, so this will be opened to the atmosphere. So this pressure of the atmosphere, we'll make that a black arrow, is pushing down. We have liquid, which is water, and we have liquid in the manometer. Obviously, that's really what we look at, comparatively speaking. And then we're going to have the pressure, the PT, the final pressure inside the container. We're going to put that right here. So PT is right there. Let's put the liquid. Now, who's winning? Clearly, atmospheric pressure is pushing the liquid back and pushing this back. So I would draw it like this. And what I just did is I've taken this suspended water by the atmospheric pressure, and I'm now just kind of relating it to a very simple manometer drawing. And if you look at here, we have the gas molecules of the butane and water trapped in this little area. Same thing here. I'll put the water here as well. Okay. And then we have the gases in the air, the nitrogen, the oxygen, and trace amounts of other gases pushing down here. Now we can see that the pressure ATM is winning. Winning by how much? It's winning by this height. Okay? So I asked you, party people, to actually measure this height from the top of the liquid to the line or to the water line. So I asked you to measure that in centimeters and convert to millimeters. Now, why do I do that? Well, the first unit of pressure was basically the pressure needed to basically what? Elevate a column of mercury fluid. That was the first manometer that Torricelli made. So not only is this pressure pushing back this gas, it's also suspending or holding up the weight of the water. Remember, the weight of the water is pushing down. So it's moving, so it's pushing the gas back, it's overtaking it, and on top of that, okay, moving this amount of water. All right, so let's just make our numbers easy. Let's pretend that was 10 centimeters. Let me pretend this height was 10 centimeters. All right, well, 10 centimeters of water is not a unit. Millimeters is closer, so we're going to convert 10 centimeters into millimeters. Pretty simple. Every 1 centimeter, there's 10 millimeters. Centimeters cancel, and clearly I'm just timesing by 10. I've got 100 millimeters of water being suspended. Now, why did I go to millimeters? Because I know millimeter unit is important with mercury, right? We don't use water. Water is not the initial unit of pressure. Torricelli made millimeters of mercury. So what do we know? We know that water is 13.6 times lighter, okay, or less dense than mercury. So we're going to have to pretend, what would this be if it was mercury? Well, it was 100 millimeters of a light compound, so wouldn't it be a lot smaller if this was a much heavier compound? Yes. So I take my 100 and divide by 13.6, and that's going to give me the height of mercury that would be suspended under the equivalent conditions. So 100 divided by 13.6 gives me approximately 7.4 Torricelli, or 7.4 millimeters of mercury. There we go. So what does that mean? Well, the atmospheric pressure is supporting this much water, so it's basically, it's pushing back the pressure and it's moving 7.4 millimeters of mercury. So we can say that the atmospheric pressure, because it's higher, because it's winning by this much, I can say the atmospheric pressure, all right, is going to be easily, I should really say, because we're going to know the atmosphere of we're going to know the pressure of the atmosphere. We're going to get a reading from the local weather station. So we're going to know this atmosphere. What we're trying to solve for is the pressure, of course, this pressure of the gases, the mixture in this container. So we're going to know this value. So what we're going to say is whatever this value is, guess what? We're going to add 7.4 millimeters of mercury, or 7.4 torr. It's the same thing. Now the only problem is, okay, I'm probably going to give you what they normally give in the station in terms of inches of mercury suspended. Yeah, that's right. Okay, we still use the English system. So let's pretend it's 29.98, okay, inches of mercury that's being suspended by the air. And you want to convert that to, well, we want to convert it to atmospheres, okay? So there's certainly some things we can do. Since we're dealing with millimeters of mercury or torr, let's go to torr first. So a very simple conversion, and again, this makes it complicated. Not really though. I know that there is 2.54 centimeters per inch, or there's 25.4 millimeters equals 1 inch. Okay, so if I was to do this conversion, I would take my 29.98 inches, and I want to get rid of inches, so for every 1 inch, there's 25.4 millimeters. So I'm going to do 29.98 times 25.4, and that's going to give me, let's just round off, makes our life easier. Okay, this is just showing you 761 millimeters of mercury or torr, and that is what our atmospheric pressure is equal to. That's given to you. So you know the pressure pushing down. This, okay, is losing by 7.4. So to find the pressure, okay, that's of the mixture of water and butane, it's the same place here, okay, what I'm going to do is subtract 7.4. The atmospheric pressure is winning by 7.4. So to find the pressure total value, in this case, I'm going to subtract 7.4. So 761, or let's take the raw number that I got, minus 7.4. And it gives me, so PT is equal to, I'll just keep it to 3 sig figs, 754. Okay, torr. So this is going to be a little less. That's why the atmospheric pressure can support some extra liquid, because it's got enough to push it back and to support some liquid. If this pressure was what? If the PT was lower, then it would be able to support even more liquid. Okay, so we found PT in my example to be 754 torr. And again, how I got to that position was to measure the height of water, consider it to be a manometer problem, knowing the pressure of the atmosphere from a given weather station or barometer in the room, and knowing how much water was suspended, and converting that into millimeters of mercury using the density of mercury and understanding what a manometer is, we got how much the atmospheric pressure was winning by. And then all I did is realize, well, that's how much this is losing by, right? It's losing the battle of the liquids. And therefore, I subtract that difference. And that's how I got 754. Now, we're almost home, okay? To get the partial pressure of the butane, all I need is the partial pressure of the water. Well, we have vapor pressure tables that someone has figured out how much pressure is due to water at different temperatures. As the mercury rises, or as temperature rises, water evaporates at a greater rate. So knowing the temperature of the water using a table of vapor pressures, we know how much pressure, or how much pressure due to water molecules is in our container. So we just look this up with the temperature. So knowing the temperature of our system, we look in the table and we find this value. So we're going to have this value. We just calculated this value by doing the manometer problem. We can solve for the partial pressure butane. That of course, you'll solve for and you'll put in here. And now we have all our values. Make sure you look at your units of R to make sure that every one of these parameters is in the same units of R, so that therefore, when you're done with this calculation, you get what? Grams over mole, and that's the lab. And whatever the value is, you can see how close it is to the 58 grams per mole that we calculated if it was pure. And that's the lab. So make sure you stop, look back of it. It's employing the use of manometer. It's employing the understanding of water being suspended in a column. Okay, we could eliminate, we'll talk about how we would. Hope this helped.